Okay, so just going to the standard control loops, and this is often at the start of your lab sheets, and this shows you how hardware is connected, but it's also a bit of a concept diagram. So it shows you the idea of what's going on, and the idea behind simple closed-loop control. So closed-loop control, we always read the block from the left to the right, input to output. We have our desired value. So in the case of a helicopter, it might be 10 meters. I want to fly 10 meters. In the case of a control rig, it might be I want the control rig to be at 60 degrees. Okay? Just a standard, wherever I want it to be. We're going to skip this for a minute. We're going to go on to the controller. So the controller is the bit that has your motor driver in and that can turn a motor, does a bit of thinking, does your program. Your actuator is your motor. In the case of a helicopter, it's the propeller spinning around. It's something that does something. It changes the physical nature of itself, either turning a heater on or making a motor spin fast. If that motor turns the propeller or whatever, it affects the output. In other words, the helicopter starts to lift off, or your pointer starts to move position, which in turn gets sensed by a sensor. So there has to be a sensor in the loop. So at the back of your pointers, there's a little potentiometer. That's your feedback sensor. In the case of a helicopter, it might be a sensor which can determine how high it is, distance, height sensor, which goes back into the loop, which is then compared with a desired value. So your desired value might be, let's say, 60 degrees. Your sensed value might be, let's say, 20 degrees. So we've got 60, and this is a subtraction, 60 minus 20. So the difference there is 40. So equivalent, a number of 40, value of 40, can go through the controller to the actuator. So you could set the motor to drive at, let's say, a value of 40% on the pulse width modulation, for example. So that could just be direct value. Let's carry on down around the loop. So let's have another snapshot in time. So the actuator is moving, so it moves more towards the desired value of 60, which is picked up by the sensor. Let's say the sensor says, oh, I'm at 50 degrees now, so it's moving, it's getting closer. Desired is 60, actual is 50, so the difference between the two is 10. So that would make the motor naturally slow down. So it slows down as it gets to its desired point, until the two values are both equal, 60 and 60, the difference is 0, so you've got 0 PWM, so your motor naturally stops, comes to a rest. So that's how a control system works. It's always continuously monitoring, just like you're driving a car. Driving a car down a straight road, you're looking where the curve is, you try not to drive onto the curve and you try not to drive too far away from the curve. So your sensor is how far am I away from that curve? That's your sensor. Your desired is how far do you want to be away from the curve? Probably, I don't know, 50 centimetres or something. So you're saying, well, I'm desired to be 50 centimetres away from the curve. What am I actually? And that difference you're actuating through your steering wheel. If there's no difference, if you're bang on, then you keep the steering wheel straight. If you're too far away, you tend to steer towards it, and too close, you tend to steer away. So that bi-directional is another thing I just want to mention. So let's say the desired is 60, but the sensor says I'm at 70. Well, subtract that and that becomes minus 10. And the minus means I'm going to drive my motor, perhaps at a pulse width modulation of, let's say, a value of 10%, but the minus says I'm going to drive it in the opposite direction. And that, when you've got your bit of code and you've got your two rungs of code, it goes down one way or the other, that is setting your direction. So that's where all that comes about when you're actually doing it. Okay, so there you go. Just looking at the motor, you've got your desired position, actual position, and your motor power. I just hide that. In its essence, the simplest form is desired position minus actual position. That's all you're doing, subtracting it. That subtraction is that bit there, but you're writing it in computer code. That's all you're doing that subtraction. And that gives you a value. We normally call it, well, in this case we call it motor power. Sometimes we call it the error. So I think in your code you called it error. Error means how far am I away from the desired value. So if I change my desired value, desired position to, let's say, 90, the motor power becomes a positive number, or the error value, which then drives the actuator, which then gets picked up. As I move it around, it changes in that way. So I'm going to give you a demo in a minute, but I just want to talk you through this demo. Let's have a look at it could be a drone height control system, or a helicopter height control system. So if we have a desired height, we've got our drone or helicopter, and it can measure its actual height. And all we're doing is saying that the rotor speed is equal to the desired height minus the actual height. So what's going to happen in this case? We desire it to be, let's say, 10 meters. It's actually at 0, so the difference is 10. So the rotor speed is going to speed up. I know 10 sounds quite a low number, but you could multiply it. But what would happen? So the rotor would turn, but then what happens when it's at that desired height? What's the difference now? So if the actual height is at 10 meters and the desired height is 10, what's the rotor speed going to be? 0, yeah. Exactly right. So it would start to fall out of the sky. So that control system does have its limitations. Okay? This is one example of how it has that limitation. It could fall out of the sky. Okay, so what might happen in reality? It would start to fall out of the sky, but as it starts to fall out of the sky, that height becomes smaller and smaller, and so the difference gets larger. So in reality, the rotors will start to speed up again. So what might happen? It won't crash down here. It will probably drop down, and the rotors will start to go faster and faster until it reaches a kind of a medium. So that it could have that, okay, and that it's meant to be there, but it's actually there. So we say that is a steady state error. When it settles down, it's supposed to be there, but the error is the difference between desired height and actual height. Steady state error. So how can we get rid of that? Okay. Something else that might happen is it might do that. So you might have the rotors and you might have a lot of inertia. So the inertia, say when I get to that desired height, the rotor stops, but inertia keeps it going. So it overshoots, gets wobbly. And I'll show you some examples of that. So on a graph, it could look like that. We've got time on the x-axis, we've got the height on the y-axis, and it's overshot and it's settled. Maybe that's where we desire it to be, but it's not quite got there. It's an underdamped system. And it's underdamped, you might think, oh, car suspension. We use dampers. It's the same thing. You push a car down, it bounces back and it oscillates. Oscillates in that same format. With your pointers, your control rig, it might get to the desired point, but it might oscillate as well. It might settle down, but it will oscillate with a sine wave. So an underdamped system looks like that. A critically damped system is what we would really like it to be. Let's say within 1.5 seconds it gets to where it needs to be and it doesn't overshoot. Or an overdamped system. Now I know these look the same, but it's actually the scale is different here. So it's taken about 5 seconds to get to its final value. So we say it's too slow. It's an overdamped system. And I've repeated it on the whiteboard here. You've got oscillation, steady state error. You've got an overdamp. You can see a steady state error. And this 3-term controller that I'm going to show you will help you solve that. So let's fire into this demo. Okay, so what I've got here is a helicopter, and it is actually it doesn't have a height sensor on it per se. I'm just using the potentiometer on the back. So as that goes up and down, you should see the orange line goes up and down, like so. Okay, at 0 it's there, so I've calibrated it, so that's actually 0, and it's flopping down so it's less than 0, which isn't ideal. Now the blue line is my desired height, so I've got a little potentiometer here, and as I turn that potentiometer, it's that green one. Okay, so that goes up and down. Actually, oh yeah, the blue line is a ground. Okay, so yes, I have, it's the green one which I'm turning, so I can say desired height, up and down. So let's say that the desired height is at 0 like that. Okay, so if I give this a bit of power and activate the propellers. Okay, so let's say I have a desired height of, and let's just do it in degrees because that's calibrated to degrees. Let's say 40 degrees. If I just move the desired one up to 40, You can hear the propellers are starting to spin. Not very well, I haven't enabled the main power. But as I lift this up, the propellers will go slower. And then as I take it, and you can see the orange just about, as it goes up to the 40, the propellers have stopped. So yeah, as you said, it starts to fall out of the ground until they start to speed up again. And it might bounce, but it might reach a medium. Okay, so that you can see how that will work. Let me just give it proper power. There we go. So, hi Dave. So what we've got, I'm giving it desired, but it has to have a big difference between before it starts to take off. Okay, there we go, and that's about as high as it's going to go. So there's a big steady state error. Not very stable, I can wobble it. Okay, doing that. So how could I make it track the value more accurately? So I've got the difference between the desired height and the actual height. Well, if I take those two values and multiply it by a value, so if I say, okay, I'm going to take that error value and multiply it by 10, let me show you what happens. Hopefully that will be the right one. There we go. So if I multiply that error value, it's got more chance, and the rotors are going faster, but it's very unstable. Okay, so we've got that multiplication. That's what you were doing in your code, in your flow code. Some of you were multiplying the error by 2 to make it a bit more feisty, a bit more, if you're driving a car, a bit more responsive. But maybe that's a bit too responsive. So if I can dampen that down, what I've got now is something that's got the same gain, got the same 10 gain, but it also dampens it. So you can see that the one at the top is the desired. It's following it. So I set it so I want it to be, what's the orange one? 30. Let's say I want, so I move the orange one so it's 30. No, it's not, sorry, the blue one's the input, isn't it? So 30, just about there. But the actual helicopter isn't there. There's a steady state error. I want it to be at 30, but it's not. But it isn't bouncing as much. I can push it away, it fights to get back, and it will stay there. Okay? So it's almost there. So if I do the last part of the controller, which is the PID, now what we've got is the blue takes off, and you can see that the helicopter is taking off and following it quite nicely. So if I move it up to 30, out there, you can see that the helicopter is fighting to the up 30. You can hear the propellers are just changing in speed a little bit. If I pull it down, speeds up, and it gets back, overshoots a little bit, but then it'll come back down. So it's constantly correcting itself. So I do that, and it will constantly correct itself to get there. If it goes too high, it'll switch off, and it'll come back down. Okay, so that demo is what we call a PID controller. So the first one, where it started not doing very well, the proportional was a low value, it was 1. When it started doing that, it was unstable a bit. I just used the proportional gain and that was 10. So it took the error and it multiplied that error by 10. But I wanted to stop it oscillating. So I used something called derivative gain. Derivative gain is also known as damping gain. So if I gave that a value of 5, what it did was it dampened it down a bit. It's called derivative because it looks at how fast it's moving. And it says, okay, apply the brakes if it's moving too quickly. So that's your derivative gain. And the last one was the integral gain. And what integral does is it removes the steady state error. So it adds a small gain to make sure that it's always on the right place. So those bits, those PID bits, you find them in the microcontroller. So you can find them in your code. So your code is actually doing this subtraction, and before your controller was just multiplying it by 2 or whatever. In this case it was multiplying it by 10, but you can also have a PID controller on here which can give you absolute control over something that's happening. So your pointer can dampen down. If it overshoots, you've got the D which stops it oscillating so much, and the I which will make sure that it's bang on that place. Okay, that's great. Thank you. Thank you.